Morning, everyone. My name is Chunyuan. Today I'll be talking about the basics of large multimodal models, and more specifically, I'll focus on a series of work called LLaVA, which will be used as a prototype and running example to show you how to build this type of models. This is today's agenda. I'll start to talk about the basics and the current status of this line of research. And on the second part, I'll introduce LLaVA 1.0, which will be the basics, and I'll go through how to construct construct the data, how to construct basic model, and show you some promising results. And lastly, I'll delve into the recent advances of LLaVA, and I will share with you the most recent research work that we have done, including how to push the performance limit, how to apply the model into different specific domains, and lastly, how we can enable new capabilities by using it as an agent to combine with different tools. Let's start with the first one, the basics. So this basics is more about the basics of LMM. I believe that most of the LLMs share very similar training objective and model architecture. Let's talk about these common points. The first one, model architecture. As you may see that most of the LLM is essentially an image to text model, right? And it takes image as input and output the language. In internal models, there are three components, including the vision encoder and the language decoder. And to collect them, we often introduce a triple module called a collection module. Also, the training objectives is always the same for LLM. It is basically the autoregressive modeling objective used in LLM. And here, the main difference is, we have to attend on the additional images or other visual signals when we generate the word. I'm going to use some examples to illustrate the basic framework of LLM. How can they be used to construct the models? Here are two more traditional models. One is GIT, and the other one is BLIP2. As you may see that the main difference is how they actually use which encoder they use, which language model they use to construct these models. And sometimes they may use very different collection modules. And both of them only takes one image as input and generate language. There's another example, which is Flamingo. And Flamingo is well known for taking into the interleave image text data. And as you can see that it also takes the three components framework that I introduced before. And there's one major difference is that its collection module is very heavy, right? And Flamingo is also well known for an interesting property because it takes into web scale interleave image text data, and it is the first model that enables the multi-modal in-class learning capability. And this, to me, is the GPT-3 moment of the multi-modal research. And last year, maybe in February or March, OpenAI introduced GPT-4V. I guess it immediately attracts a lot of attention, and people are curious that how OpenAI construct these interesting examples and these interesting scenarios. And it does not belong to any traditional academic tasks data set. And I think most of the community get very curious how they actually build such models. And also in last year, I think there are a lot of work trying to illustrate how to construct the data to build the basics of such models. And this is my observation for last year and this year. And last year, because we start from zero and the community is interested how to build GPT-4V-like models, right? Including how to construct data, how to construct the model, the basic model, and how to do the evaluation. And we do see a lot of interesting work that enable new capabilities. These can be viewed as different prototypes. But last year, also in this tutorial, I mentioned that it is true that we made a lot of progress in terms of prototyping, but there's a large gap remains when we talk about scaling the capability to certain performance limit. This is the example that I used last year, right? We see that when the open source model trying to read the papers, it has some challenges. And this year, I saw a very different phenomenon, which is first, it almost agreed that how to construct the LLM, right? If you look at a lot of papers, they'll share a very similar training recipe. And the second observation is that it seems that on a lot of benchmarks, and there are many open source models that has already reached like 90% performance of the GPT-V model. But when we talk about the in-the-wild capability of these models, it still shows some limitations. So I'll start to talk about my observation in the language space. In language space, there is also a kind of competition between the private model and the open model. And so GPT-4 inherits the capability of GPT-3 and further introduce the instruction following capability that becomes the foundation for ChatGPT. And in the open in the language domain, we also see a lot of open models, including Llama and Mixture. And they also last year we are talking about GPT 3.5 GPT 3.5 performance, and this year I think people are talking about can we reach GPT-4 level performance in language domain. And in the multimodal space, and as I mentioned that if we view Flamingo as a GPT-3 movement for multimodal research, and now when we are talking about the GPT-4V or GPT-4o like models in the multimodal space, there are a lot of private models, and also there are a lot of open models. I will not dive into the details of each of the individual models. I just to show you that the open models, and they are quickly catch up in terms of benchmark results, at least in terms of benchmark results. And I think the community also realized that it doesn't mean that we are doing so close with the open models, but it at least give us some measurement to measure the gap between the open model and the private models. I believe you also noticed a debate in the community. There are two different ways to treat LLM. One is a current, one is the stage-wise training, and the other one is training everything from scratch. And most of the recent work, most of the research work, they focus on the stage-wise training and also show some promising results. And I think it means that if you take a look at the current recipe, right, we always like start from a pre-trained vision encoder like CLIP. We always just start with a pre-trained language model such as Llama, and build on top of these two pre-trained models, and then we introduce the collection module, and which is training from scratch. And then we put everything together and training it on image test data, and then we get models like LLaVA, which performs well on several benchmarks. And I think one reason like this kind of model become popular is that it requires less compute, right? I think meanwhile people are very curious how the performance will be if we train everything from scratch. But honestly speaking, almost like there are only a few labs in the world that is able to do it, right? And today, This tutorial will be focusing on the first type of work, which is stage-wise training. Now I'm going to dive into the second part, which is how to build the basics of LLM, which I'm going to use LaVA. Let's start with a story in the language space. And so there's a concept called self-instruct, where you use like examples including instructions and responses. And then you use examples as an input for LLM and ask the LLM to generate similar instructions. And by doing this, we are able to generate a large diverse set of language instruction following data, which can be used to train LLM. Okay, which can be used to train the open LLM model. And it is natural to borrow the idea from the language domain to the multimodal space. Even though the idea is straightforward, and there's a unique challenge in the multimodal space. Remember that our teacher model is a LLM, which can only takes in language, right? But when we talk about multimodal models, the input include both image and text, and the unique challenge is how we actually represent the image so that the language model can understand. And we introduced LaVA, and the first problem with that we will solve is how we actually represent the image so that with the LLM can understand. So here's one example. On the right part, this is the original image, which is a pixel represented images like the raw image. And in the research community, and we have a lot of rich annotations to represent the image. And here we use two types of representations. One is caption, and if you think about caption in the MX Coco, right, it's there for each image there are 5 different captions, and each of them is describing the image from different perspectives. And we believe these captions provide rich representations of the original image. And on the other hand, we will be using the bounding box in object detection as the other set of representations. And typically, the object this will be including the concept and the locations of the main object represented by coordinates. And we believe that the caption and the box can be used as a representation to approximate the original image, and we use them as an input for LLM for in-context learning. And by doing that, we are able to generate the multimodal instruction following data. I'm going to use here we provide the 3 types of instruction following data. The first one is a multi-turn QA. It's basically like describing talk about the attributes of the objects in the original image, and it is generated to accommodate the scenarios like daily life scenarios where we typically ask the basic content of the image. And second type of instruction following data is detailed description, where we want to describe the image as detailed as possible. And last one, we call it complex reasoning. It is not only about the content of the original image itself, it's more about the implications of the original image. In this example that we see a small SUV and several luggages. And here the question is, what challenges do these people face? And in the answer, we say that the challenge is how can we put all these luggages into a small SUV, because the SUV is small and there are many luggages. And so these 3 type of instruction following data will be used as a diverse instruction for us to train the LaVA model later. Now let's talk about the architecture. So LLaVA is probably the simplest model architecture you will see for LMM. So as we mentioned before, it also follows the three-component framework of LMM we introduced earlier. And here we use the clip vision encoder to understand the image, and we also use the Vicuna model as the LLM to generate language. And the only trainable parameter we introduce is a linear matrix. We call it a projector, which is used to collect the vision encoder and the language model. So to train it, we introduce a two-stage training strategy. In the first stage, and the main goal is to align the vision and the language features. And we freeze all the model parameters. The only trainable parameter is the projector layer that we introduced earlier, right? And we think about it, even though the entire system has a lot of trainable parameters, and the only trainable parameter is a simple linear matrix. And then by training it on a subset of C63 media, and we are able to align the image text features. In the second stage, and now we are going to train both the projector and the language model. And we will train it on the multimodal instruction following data that we introduced in the last slide. And remember, there are a diverse set of instructions that we introduced earlier. And by training the model on these diverse instructions, then the trained model will be generalized to understand a lot of unseen instructions in the real world scenario. Here I'm going to one classic example. And remember, this is one example showed in the GPT-4 paper. And I promised to you that LLaVA will be able to reproduce this example for the first time. And here we show the example. And in this classic example, the question is, what is unusual about this image? And we see that the man is doing eye rolling. Eye rolling is typically an indoor activity, but now the man is doing it on a movie taxi, which is unusual. And we see that LLaVA is able to produce this example, and is also able to provide more details of this image. And this is also showed by the GPT-4 paper. I'll talk about interesting. We also observe several interesting emerged capabilities of the original LLaVA model itself. Here, I mainly highlight one emerging capability, which is the zero-shot OCR capability. Remember, in our training data, we use a subset of CC and the multimodal instruction following data that we construct. And there is no OCR data at all in this in the training life cycle of the LLaVA model itself. And interestingly, we see that the model can do zero-shot OCR. Let me use some examples. This is the CVPR logo last year, and we uploaded the image, and the model is able to see the word of Vancouver, Canada. It also provides the implication that maybe people in AI and its applications will be interested in this example. And here's another example. This is the CV in the wild workshop logo that we are also hosting right now. And the model is able to see the entire sentence, the computer vision in the wild. And last example is the example that I wrote by myself in the evening that we released LLaVA. And we see that the model is able to see the new word LLaVA itself. So this is exactly the slide that I used last year, CVPR, the same tutorial, and that where we see that GPT-V indeed, attract a lot of attention, and people start to take a look at this research topic, and we introduce LLaVA and almost concurrent with mini GPT-4, which are open source models trying to replicate GPT-V performance. And immediately that we see a lot of work in the following months. I think now it is like 1 year, right? I believe you already see that there are a lot of work on this research topic. And if you view that last year that we planted a seed and now there is a tree. Maybe there's a small tree last year. Now it's a big tree. I believe it will grow bigger. Okay, last part, I'll introduce the recent advances of the LLaVA family. Starting from last year, and we continue to build together with the community to enable its capabilities and improving its performance. So here I'm showing the timeline of the LLaVA project, where I highlight some of the milestones. And so I will categorize this project into 3 classes, including performance, applications, and new capabilities. And then I will dive into each of them. So to talk about the performance, remember that LLaVA 1.0 is just a prototype to show you how to replicate some examples of the GPT-4V, right? If we talk about the performance comparison between open source model like LLaVA and the private model like GPT-4V or 4o, I believe last year there's a big gap. But meanwhile, the community is working hard to catch up. And this is going to be the performance part that I will talk about. And second part is application. And this community, the CVPR community, is mainly focused on the general technology itself. But I believe the techniques are also used in some vertical domains, such as healthcare. I'll show you some examples there. And lastly, new capability. And when we talk about LMM, now it is mainly image text task or model. But I believe in the future, and there is a chance that we can unify every single vision task in such a framework. I'll show you some of the examples there. Okay, let's talk about the first part. Okay, this should be 3.1, where we are going to dive into the model family, trying to push the performance limit of the LLaVA family. I'll talk about LLaVA 1.5 first, and then LLaVA-NeXT, and then we build several variants of LLaVA-NeXT models. Okay, first, LLaVA 1.5, which was released in September or October last year. And this is also presented in this year's CVPR in this Friday. And I will not talk a lot of details of LLaVA 1.5. I think the main difference is on top of LLaVA 1.5, we add a lot of academic data into the data mixture. The reason is, when we developed the first version of LLaVA, our goal is trying to build a chatbot, right, where the model can be used as an assistant to talk about the image with humans. But now, there are a lot of concurrent at that time, where they trying to push some of the benchmark results, and we realize there's a gap between our model and the models that are trying to push the performance limit on the benchmarks. We think this is a good idea if we could, further use the academic data and trying to push the performance limit. And this is the main motivation. And we're trying to, borrow a lot of data set in the Instructor Belief paper. But we also realize a problem if we directly borrow the data, and we see that there's a lot of conflicts between different task instructions. It means that given one image, given the instruction, the model will be confused which task which task the model should perform or how to perform the task. That's why we add we add some clarification or formatting prompt so that the model can be better guided when completing the task. This is about the data construction. And eventually, we increased the data mixture from 158K to something like 600K. And with this new data mixture that in last October, we see that the LLaVA 1.5 model is able to achieve state-of-art on a dozen of benchmarks. And we also only use maybe like less than 100% of the original of the training data set of other models. And this January, this year, we introduced a next version, which is called LLaVA-NeXT. And there are three techniques that we build into LLaVA-NeXT. The first one is any res, which means that, remember in the previous LLaVA model, we only take images of resolution like 200 or 300, and we also notice that it is almost true that the performance will be increased if we could further increase the image resolution. But the challenge is that in the open domain, the clip model or the open clip model can only take images of limited resolution. And we are thinking how could we further scale up the image resolution. And this comes to the dynamic high resolution strategy where we introduce any res. So there are two ways that we can encode an image. One is the original path, and the other one is we can divide the image into multiple patches, and for each patch, we will feed the patch into the original VIT and trying to get a sequence of tokens. And after doing that, we will concatenate all the VIT tokens together into one vision sequence. This sequence will be long, it's true. And then we will feed it into LLM. This is the first technique. And then as you might realize now that data is the most important thing for training LMM, then we further increase the data mixture, improving its quality. And last one is LLM itself is also important. And because we have a little bit more compute, and now we can scale up the LLM and use the best LLM at that time, which is the E model. Combine these three techniques together, we introduced LLaVA-NeXT, and it was shown that in this January, the LLaVA-NeXT model can catch up Gemini Pro on selected benchmarks. And you can see that the compute is not that heavy, right? With 32 A100 GPU and training it in one day, and we will get such great performance. So we further push the model performance, and with more compute, and now we are able to train larger models, including the model size like 110 billion. And these models are released in this May. And we see that if you look at the model performance of 110 B, if you look at all these benchmark results, it's getting very, very close to GPT-4V. So this is done by simply increase the LLM size, and the model recipe remains the same with the recipe that we released in January. And if you look at the computational cost, it's like 18 hours on 128 GPUs, right? It means that it's actually not that challenge if we want to replicate GPT-4V, at least in terms of the ideas and the training recipe. And we further show some insights. And if you look at the LLaVA-NeXT training recipe at this point, and the only thing that we do is to trying to using stronger LLM, and we see that the performance will be improved, right? And that's why we summarize this as stronger LLM supercharged multimodal capabilities in the wild. And there are some detailed studies there. The basically is, if you have a stronger LLM, then it is much easier to build a stronger multimodal models if you have the compute to convert it into its multimodal variant using LLaVA-NeXT training recipe. And here are some further detailed application study we did for LLaVA-NeXT. And we will talk about it in 3 parts. The first one is architecture. Remember the 3-component framework we introduced in LMM, right? It's including pre-trained LM, it's including pre-trained vision encoder. And what if we change the model architecture a little bit, trying to increase the scaling the language model or trying to scaling the vision encoder? So the first observation, which is about the scaling the language model size. And we scaling the LLM size from 0.5 billion all the way to 110 billion. And it is said that this LLM scaling is very, very effective for achieving great multimodal performance. And on the other hand, what if we scaling up the vision encoder size? And we tried a lot of existing vision encoders. And we also, the largest one we tried is the 10 billion version from EVA. Well, the story is different. Scaling up vision encoder size is not that effective comparing with the training data and the visual representation of the vision VIT itself. I think this is a problem for this community, and how can we construct a better VIT or vision encoder for building better LMM. And the second insight, which is about vision representation. How can we represent the visual signal itself? I'll decompose visual representation into 2 parts. One is the original image resolution, and the other one is the number of visual tokens we use to represent the original image. Both of them can be scaled up, right? And it is almost true that you will get better performance if you're scaling up either the resolution or the number of tokens. And in the original LLaVA-NeXT recipe, and we have a limited configuration to digest the original image. Now we're trying to do it more aggressively and further increase the number of grids in the recipe, which can take into higher resolution images, and then we compress it into a smaller number of visual tokens. And with variance experimental results that we see that scaling up both resolution and the number of tokens can increase the performance. And there is also recommended configurations. And last one is a training recipe. And for the 3 LLaVA variants that we introduced earlier, that you may say that the only part that we play with is the last stage, the visual instruction tuning stage itself. And for other parts of the pipeline, it remains less explored. And now we show that it is actually very, very promising if you try to inject high quality knowledge into the LLaVA training recipe. For example, if you use some of the public image test pairs in pre-training, and if you only train the projector or if you train a full model, you will see that the performance improvement is very limited. But instead, we show that if you could use the previous LLaVA to generate high quality captions and use these high quality captions to do your full model training, and then you will get a significant performance improvement when doing visual instruction tuning. And by averaging on several benchmarks, we show that by doing so, we could improve the model performance by 3 points. And if you are wondering which where is a high quality data, we open source those data sets on Hugging Face. So we did a data set including COCO, Belief, and the CC3 media, and those are common data sets that we use in the vision network community, and we believe that the high quality caption provided by the LLaVA model can be used to train better vision network models. And now we extend the model into video. And remember, we introduced the AnyRes technique to digest the images, right? For each image, we will use several patches and to fit it into VIT and further fit it into the LLM. To LLM, it actually sees several images, right? And this AnyRes technique can help us naturally, transfer the model that we trained onto the video domains. Because for videos, it's naturally a set of frames, right? So this means that the image trained LLaVA can directly perform the tasks on video. I'll show you later, the performance is actually great. But remember that we only in the training part, we can only see like a small number of images, right? In the inference time, how can we digest long videos? And we use the technique called length generalization, where you can play with the position embeddings so that you can digest the longer videos. And we also build a technique DPO on the video tasks, and put these three together. I'll show you some of the performance on video tasks. Let's look at the 7B model first. So the image trained LLaVA itself can become the state-of-the-art model in the open source domain, which performs better than the previous video LMM models. And if you do it with DPO, and you will see significant performance improvement. And this is the observation on the 7B model. And if further increase the model size, in the 34 billion model, it can achieve similar performance compared with the Gemini models on some of the video benchmarks. And you may notice that there is a video MME benchmark released a couple of weeks ago, and LLaVA-NeXT was the state of art until yesterday when I did make this slide. And there's a new model called VLA 1.5, and which will become the new software in the open domain. We further introduced LLaVA-NeXT interleave, and in the previous LLaVA series, the model can only consider one image as input, right? And I believe, at least on the GitHub issue that we see a lot of requests, can LLaVA digest multiple images? And we extend the capability into the multi-image domain. And we also noticed that this interleave image text format can naturally, digest many other tasks and scenarios, including 3D, video, and images. And we construct data set and put all this training data together. And we also construct a evaluate data set to evaluate the multi-image scenario. And turns out on the multi-image evaluation, this model, the new model, can outperform the previous Sultan, the Mantis model. And if you look, we can also take a look at the performance on video. And this new model also outperforms the LLaVA-NeXT video model that we introduced earlier. And lastly, the 3D evaluation, and we see that it is better than the point representation or other representation of the 3D scenarios. And there's one emerging capability that I want to show that, remember, we only have the multi-image and data, and we also have the video data, but there is only one video every time when we train the model. And if we, by doing task composition, that we can see the model emerge some interesting capabilities. For example, in the inference time, you can ask the model to compare the difference between two videos. This is an unseen task, and the model can generalize to this unseen task. And if you are interested in this live research on LLaVA-NeXT, and we have a blog post and where you can track the recent progress. And I want to also show you that this is the LMM evaluation pipeline is a pipeline that we use to develop LLaVA model. And as now you may realize that there are a lot of benchmarks, right? After building one model, if you want to build a model, evaluate the model on multiple benchmarks, and I think this evaluation toolkit will be very helpful. And it is the toolkit that we use to develop these LLaVA variants, and it is also open source. Now we'll talk about applications of the LLaVA variants. First one is LLaVA-NeXT, and it is actually built in last May. After we built LLaVA 1.5, LLaVA 1.0. So so how can we actually convert the general domain LLaVA into the domain specific ones? And I think after a lot of experiments, the conclusion is so we will need to construct the domain specific multimodal instruction following data itself, following the framework that we introduced earlier. Use some of the image test pairs to construct the question answer pairs. And on the bottom left, we constructed the LLaVA-MED instruction following data, and we use this data to train the model. And there's an interesting behavior of the trained model compared with the general domain LLaVA. So if you ask some medical related questions about the general domain LLaVA, and the model will either hallucinate or trying to refuse to answer the question just because there is no domain knowledge. But if you ask the same question about the domain LLaVA-MED, which is a domain specific model, and model will trying to respond, at least trying to provide some ideas of the medical domain answers. And the team also further extend the LLaVA-MED model into one more specific medical domains, which is the radiology. And it showed that if you further use domain-specific data and train the model, and you will get a better performance on such vertical domains. And lastly, I'll talk about the new capabilities. And remember, in this part, we are not going to build the end-to-end model. Instead of that, we will use a pre-trained model and the other pre-trained model together to construct systems. And the first one is a LLaVA interactive system. It is not an academic paper, and it's not an academic project. It's just a demo that we put the pre-trained model in our team together, and trying to show you that how we can achieve interesting applications if we use the pre-trained models. And so more specifically, we use 3 models. The first one is LLaVA for visual chat, and also glitching for grounded generation and editing, and also the same model for interactive segmentation. So you may view this more like a product prototype, and a user can generate or upload an image, and then you can use the 3 mode that I introduced before to interact and play with the image. I'll show you some one interesting scenarios. So let's say we upload an image like the one on the top left, and then we ask the demo what part can be improved visually so the model will respond, say that there is a pier in the middle of the image, and it will be great if you could remove the pair. And we follow the instruction and select the pair in the middle, and then drag this pair out of image, and then we get a clean image. And after doing that, we can further ask the question, which part can be removed? And it might be too small, and the model response say that there is something in the middle of the lake, you can further remove it, and we follow the same instruction and remove the little thing in the image. And after doing that, we ask the model, what can be added to improve the visual quality? And model suggests that you can add some, sunset in the sky. And we did it. And then we ask the model, how about the current image? And the model will say that, this doesn't follow common sense because there is a sunset on the sky, but there's no reflection in the lake. And we follow instruction and then further add the reflection using a grounded editing capability of the system. And then we get a final image. And then the model is satisfied with that. So this is just one interesting scenario that if we could really achieve the true multimodal system of, hello. Okay, it works. Thank you. Okay, great. We get the final image and the system works in many sense. Okay, now you can see that this is one interesting scenario, right? But remember, this is not one end-to-end model. It's just a system that we put 3 pre-trained models together. But at least it show you that, show to this community that, this is something that we could do in the future if we build one model to achieve such scenario, right? Okay, I'll talk about the last word, LLaVA-Plus. And it's about how we use the LLaVA model to use more tools to completing more tasks. And remember in the original LLaVA model, and when there comes an instruction, the model will use the internal knowledge stored in the model weights and trying to respond to the instruction, right? But the knowledge is limited. And there are limited skills of the original model if we only leverage the knowledge in the model weights. And we notice this limitation, and then we introduce LLaVA-Plus, which where we introduce a concept called a skill repository. It is essentially a set of pre-trained models, a set of vision experts that are designed for different scenarios or that are designed for different tasks. And it includes models for visual generation, visual understanding, and interaction. So now the system is when there comes an instruction, if the model feel like the system is requires some of the external knowledge or skills to completing this task, it will trigger the corresponding tools and then trying to get to output and aggregate the results with the previous history as an output, the answer. So it's very similar to the current web design, right? And if you need some, detailed knowledge, you need to, interact with the database to get the related knowledge. And we borrow this concept for the multimodal space and construct the LLaVA-Plus model. So and there are not, by doing that, we are able to achieve more interesting capabilities. I will now dive into the details. This is the one example to show that by calling the object detection tool, now we can provide an accurate bounding box position of the object, and with this additional information, the model is able to provide a more accurate response. And these techniques can be also used to doing web search and then doing image generation and the editing, and even help you to post your Twitter post by composing all these tools together. And this last slide where this is actually the survey paper we did last year for this tutorial. And if you are interested in the basics and the recent advances and want to learn it offline, I will recommend this survey. Thank you.